Here in this section, we have alternating series and conditional convergence. The first part here, we have theorem 15 on the alternating series test. Here we have the series that says a sum of -1 power n plus 1 times u sub n, and is from 1 to infinite. This is equal to, so starting from 1 for n, we're going to have u sub 1, and coefficient of u, here we have -1 power 1 plus 1, so we're going to have 2. -1 power 2, that will be positive here on this part. The next one, n equal to 2, so we have u sub 2, and then here we will have 2 plus 1 for power, so that is 3. We have -1 to the third power, so that is negative. So that's how here we have negative u sub 2. And then again we have positive, again we have negative. So we have u1 minus u2 plus u3 minus u4 plus, so this goes to infinite. So here we used 3 dots. So this series converges if the following conditions are satisfied. Number 1, the u sub n's are all positive. Number 2, the u sub n's are eventually not increasing. So what that means, u sub n greater than or equal to u sub n plus 1 for all lowercase n greater than or equal to uppercase n for some integer n. Number 3, u sub n approaches to 0. Theorem 16, the alternating series estimation theorem. If the alternating series sum of -1 power n plus 1 times u sub n, and from 1 to infinite, this is exactly what we had on top. So satisfy the 3 conditions of theorem 15. So if the series satisfy the 3 conditions of theorem 15, then for lowercase n greater than or equal to uppercase n, s sub n is equal to u sub 1 minus u sub 2 plus, I use 3 dots here, plus -1 power n plus 1 times u sub n. So this part is what exactly we have here on this part. So S sub n approximates the sum L of the series with an error whose absolute value is less than u sub n plus 1, the absolute value of the first unused term. So sum L lies between any two successive partial sums S sub n and S sub n plus 1. For example, here we have, if we use n equal to 2, we're going to have S sub 2 and S sub 2 plus 1, so S sub 3. And here we have these two. And L lies between S sub 2 and S sub 3. And that is same for S sub 4 and S sub 5. So after that, we're going to have S sub 5 here. So L is here between these. And the remainder L minus S sub n has the same sign as the first unused term. For example, for n equal to 1, having L minus S sub 1. For that part, we're going to have same sign as u sub 1. And that is positive. Definition of series that is convergent, but not absolutely convergent, is called conditionally convergent. Theorem 17, the rearrangement theorem for absolutely convergent series. If sum of a sub n and from 1 to infinite converges absolutely, and b sub 1, b sub 2, to b sub n, and this goes to infinite, is any arrangement of the segments a sub n, then sum of b sub n converges absolutely, and sum of b sub n and from 1 to infinite, that is equal to sum of a sub n and from 1 to infinite. Now here on this part, we have n term. We had some of these before. So number one, the n term test for divergence. Unless a sub n approaches 0, the series diverges. Number two, geometric series, sum of a times r to the n power converges if absolute value of r less than 1, otherwise it diverges. Number three, p series, sum of 1 over n power p converges if p greater than 1, otherwise it diverges. Number four, series with non-negative terms. So for this part, try the integral test or try comparing to the non-series with the direct comparison test or the limit comparison test. Try the ratio or root test. Number five, series with some negative terms. So on this part, that's the series absolute value of a sub n converge by the ratio or root test or by order of the test listed above. Remember, absolute convergence implies convergence. And finally, what we had in this section, number 6, alternating series, sum of a sub n converges if the series satisfies the conditions of the alternating series test. And those conditions are these three from this section. Determine whether the alternating series converges or diverges. So here on this part we have sum of -1 power n plus 1 times n over 7 times n to the 7th power plus 1, n is from 1 to infinite. So based on what we had in Turing 15, this series converges if we have all these three conditions. So UNs are all positive, UNs are eventually non-increasing, and UN approaches to 0. So for the first condition, here on the spot they have starting from n equal to 1 up to infinite. So n equal to 1 and increasing to infinity. What we have for u sub n in this case is this part, n over 7 times n to the 7th power plus 1. This part is always positive because n is always positive. So n is from 1 to infinite. So u sub n is positive. In order to determine whether u sub n, which is n divided by 7 times n to the 7th power plus 1, is eventually non-increasing, define f of x equal to x over 7 times x to the 7th power plus 1 so that the values of f match the values of the sequence at every positive integer n. Now find first derivative of f, so that is equal to derivative of what we have in numerator, that is 1, times what we have in denominator, so 1 times 7 times x to the 7th power plus 1, which is this part. And then subtract, find the first derivative of what we have in denominator, that is 7 times 7, it's 49, times x, power will be 7 minus 1, so that is 6 here on this part. And then multiply by what we have on top in numerator, so multiply by x. Denominator we will have 7 times x to the 7th power plus 1 squared. Now simplify. So we have 7 times x to the 7th power plus 1. Now combine these two. So here we have x to the 6th power. Here we have x power is 1. We have multiplication on that part. We have same base. We should add powers. So we're going to have negative 49 times x to the 7th power divided by what we have in denominator. And then here we have like terms. So we have negative 49 plus 7, that is negative 42 times x to the 7th power. Then this one, add 1, divided by what we have in denominator is 7 times x to the 7th power plus 1 squared. So based on what we had for first derivative of this function, negative 42 times x to the 7th power plus 1 divided by 7 times x to the 7th power plus 1 squared. This is less than equal to 0 for x greater than equal to 1. For example, if I had 0 here on this part for x, this will be positive. So that's why here I have x greater than equal to 1. So starting from 1 for x, using 1 here, we're going to have negative number on this part adding 1. This part, numerator will be negative. So that's how this is negative. So we have less than or equal to 0 for first derivative of this function if we had x in greater than or equal to 1. What that means, the positive u sub n's are eventually non-increasing. So we have the first condition, second condition now here for condition number 3. We should evaluate limit of u sub n, which is n over 7 times n to the 7th power plus 1, and approaches infinite. So this is equal to 0. Because here the power that we have in the denominator is 7, that is greater than what we have on top. This is 1. So having infinite for n, limit is equal to 0. So this means u sub n approaches to 0. So we have all 3 conditions for the alternating series test. What that means, the series converges. Does this series converge absolutely, converge conditionally, or diverge? So here we have sum of negative 1 to the n power times n to the 7th power times 2 over 11 to the n power, n is from 1 to infinite. So I have this one here before finding the answer. A series sum of a sub n converges absolutely if the corresponding series of absolute values sum of absolute value of a sub n converges. If the series converges but is not absolutely convergent, then the series converges conditionally. Otherwise, the series diverges. So find the terms of the corresponding series of absolute values. So absolute values of what we have here on this part, absolute value of negative 1 to the n power times n to the 7th power times 2 over 11 to the n power, that is equal to positive n to the 7th power times 2 over 11 to the n power. Now use ratio test to see if series converges or diverges. So finding a sub n plus 1 divided by a sub n, that is equal to, using what we have here on this part, starting from here, instead of n on top numerator, we have n plus 1 to the 7th power times 2 over 11. Here on this part, instead of n, we have n plus 1, so power in numerator, that part is n plus 1 divided by what exactly we have here on that part, that is a sub n, so n to the 7th power times 2 over 11 to the n power. Now simplify. So this is equal to n plus 1 over n to the 7th power. We have 7 and we have 7, so same power. Multiply. Here power is n plus 1, denominator power is n, and we have same base, and that is 2 over 11. So writing 2 over 11, and because of having division, we should subtract powers. N plus 1 minus n power is 1. So using the ratio test, what we have for absolute value of a sub n plus 1 over a sub n, that is equal to positive a sub n plus 1 divided by a sub n, because of having this here on top. So absolute value of that part is equal to what we have here, which was positive. So we use that one, and for ratio test, we have this part. So this is equal to n plus 1 over n to the 7th power times 2 over 11. So next step, evaluate the limit of absolute value of a sub n plus 1 over a sub n as n approaches to infinite. And here for absolute value of a sub n plus 1 over a sub n, we have this part. So limit of n plus 1 over n to the 7th power times 2 over 11 as n approaches to infinite, that is equal to, so move this to left side. This is equal to 2 over 11 times limit of n plus 1 over n to the 7th power as n approaches to infinite. And this is equal to 2 over 11 the series of absolute values converges because based on what we have here, 2 over 11, that is less than 1. What that means, the given series converges absolutely because the corresponding series of absolute values converges. Does the series converge absolutely, converge conditionally, or diverge? So here we have sum of -1 to the n power times n plus 5 to the n power divided by 7 times n to the n power n is from 1 to infinite. Find the terms of the corresponding series of absolute values based on what is given here on the spot. Absolute value of -1 to the n power times n plus 5 to the n power divided by 7 times n to the n power, that is equal to, so here we have positive n plus 5 to the n power divided by 7 times n to the n power. So what we have here on this part, for numerator denominator, we have power n. Because of that, I'm going to use root test. So use root test to determine if series converges. So first find n root of absolute value of a sub n for the series n plus 5 to the n power over 7 times n to the n power n from 1 to infinite. So a sub n is what we have here on this part. So n root of absolute value of n plus 5 to the n power divided by 7 times n to the n power, that is equal to, so canceling these because of having n root. This is equal to absolute value of what's left here is n plus 5. Denominator we have 7 times n. Now find limit of n root of absolute value of a sub n approaches to infinite. So here we have limit of absolute value of n plus 5 divided by 7 times n as n approaches to infinite. And this is equal to, here we have 1 times n, so that is 1 over 7. And this is less than 1. So 1 over 7 less than 1 using root test. This means the series converges. So this series converges, therefore the given series converges absolutely.